Hola, this is Joe Brucey, developer of PA Calculate, the calculator app for pro audio and lighting applications. This is a video tutorial on the array modeling capabilities of PA Calculate that have been recently added asteroids to. Before we had just a simple inline modeling, now we added broadside as well as a lot more graphical and practical capabilities to the calculation engine in general. So starting with inline, we have of course two types, endfire and gradient. With inline arrays, we space the elements actually. This would be the direction that the sound is going. If you had a stage here, then the public would be on the right hand side. So we can change the number of sources and we can change the spacing. Okay, if we go to the simplest of the arrays with just two elements, then we can see that here we get the frequency that corresponds to a quarter wavelength. In this case, this is 21.64 Hertz, and that would be for a temperature of 20 degrees centigrade, which is 68 Fahrenheit. If you change this temperature, of course, speed of sound changes, and that frequency changes as well. Okay, this frequency will show up here in the frequency response front to back. That's the ratio between what's happening at the front and what's happening at the back. And that's all fine and dandy. The thing is, that only happens at the very back of the array. If we click on this radio button, then we get to see 0, 90 degree and 180 degree frequency responses relative to the number of sources. So in this case we have two sources, so the maximum here will be 6 dB. The red is 0 degrees because with endfire arrays we use delays such that all of the elements arrive here at the front at the very same time. So that's why we have perfect summation. That's the red line there. At the back we have this notch at 71 Hertz, and on the sides though this notch happens at the frequency that's twice as high, 142 in this case. That's because if we are here in the back of the array, we have two sources of delay, one being the physical separation and one being an electronic delay. If we are on this side, we just have the electronic delay, not the physical separation. Therefore, this notch happens here at a frequency that's twice as high. Okay, one important thing is that the spacing is the distance between the same part of the array, the same part of the element and the adjacent element. So between front rail and front rail, or back and back. The spacing is not the space between the boxes. Okay, so the way endfire arrays work is that we align all of these elements so they arrive at the very same time at the front. We do that using delay. The largest delay would be for the front box, and finally the back box wouldn't have any delay at all. We can see the what's happening here. A has 0 and H has 24 milliseconds of delay, corresponding to the to this space here. This dotted circle that you can almost see here at the back shows you the virtual origin of the elements. If we give it some rotation, it's a little bit more clear. We can see a dotted circle, which is the virtual point of origin for each of the elements as seen from the front. Okay, we can also do gradient arrays for 2, 3, and 4 element arrays. In this case, what we do is not align at the front, but align at the back of the array and invert the back box. That way we theoretically get complete cancellation here, which is this notch in this polar plot, which is the familiar heart-shaped or kidney-shaped polar plot. We can also see this as a coverage map, and again you see a relatively familiar picture. Okay, like we said, the back box has inverted polarity, and this is shown with a black border here. On the table we can also see it very clearly. The back box has both delay as well as polarity inversion. There's also an unusual type of cardioid or gradient, rather in this case second order gradient configuration that we have here. And this is unusual, but it was already described by Harry Olson many years ago. Basically, we have this element which has no processing, no delay, or polarity reversal. These two middle elements have both delay and polarity inversion. And finally, this end element here has only polarity inversion. We can see what's happening here. Okay, so this gives us more side attenuation than a cardioid would. So, for instance, if we take away the rotation, we can see the difference very clearly on the polar plot. Polar plot for a cardioid has very little side attenuation here, and you can compare it to this. Okay, so the original description of this array is for this square arrangement here that results in a 45-degree angle. That's only useful if you do left and right configurations. But in the app, we do this kind of rhomboid shape, which is basically the same thing, but just rotated 45 degrees, so you can use it straight if you want to. Okay, one of the graphics that we have available here is the isobar display, which is very useful to give you a quick idea of what's happening in the whole of the frequency range, not just a single frequency. You don't have to cycle through the different frequencies. So, for instance, here we can see that with this 4-element gradient array, we have a fairly constant pattern up to 140 Hertz or so. The frequency that's shown here on the pole plot is noted by this small arrow or triangle here on the isobar display as well as the frequency response. So if we now change to a 2-element cardioid, you can see that's a lot wider, but also fairly constant with frequency. If we switch to Empire, then we can see that we have an omnidirectional response at the very low end, and we can see the polar plot here. As we go up in frequency, we start getting some directivity. So we can see that here, that's the main lobe, which corresponds to this main lobe here. As we go up in frequency, then we'll start getting more lobing, and eventually this figure of 8 kind of a pattern. Here the notches correspond to these roughly 90-degree notches that you can see here. If we had a constant beam width, like a horn that has a constant coverage angle, then this kind of rectangular part would extend all the way to the low end, where we have a rectangle with this kind of a shape. Just to give you an idea, to help you understand what an isobar display is, if you're not familiar already with it, although it's become fairly common in array specifications depending on the manufacturer. Okay, so that's for 2 elements. If we switch to 8 elements, you can very easily see that the whole frequency range became a lot more narrow. So again, it's a very quick way to give you an idea of what's going on throughout the frequency range of subwoofers in this case. Here we're plotting from 20 to 250 Hertz. Okay, so that's Empire, and lastly we have this field here that allows you to enter an additional delay, which is useful to be able to align the subwoofer array to the mid-high line array. Okay, so let's now go to, okay, before we do that, just a note on frequency responses. If we switch the isobar display off, calculations will be faster. Okay, let's go back to just a simple 2-element array, and we see these notches. There's a finite resolution that we use, so depending on the frequency that this notch happens to be at, it might show as deeper or not so deep. Here basically we're looking at the same thing, but the resolution, the frequency resolution, may catch this very peak in a different way. So just bear that in mind, that the depth that you see here may not be exactly what's going on. It might be deeper. On the other hand, distance does have a major effect. If we are very close to the source, then the first element will be very, very close, and the difference in distance between this element and this element will be very large if you are close, whereas if you are very far away, then the difference is very, very small. If you are at, say, 100 meters, then one could be at 100 meters and one could be at 101 meters. So you'll be able to get basically the same level and therefore deep notches. Okay, so if we say change this to 10 meters, then those notches are less deep. When you think about the what's happening at the very back. If we look at front to back ratio, then we can see that very well. If we change this to 5, the attenuation here, the notches will be even less. Okay, so let's now go to broadside, and now the elements are spaced perpendicularly to the radiation axis. So basically, when we add elements, we get directivity on the side, but not front to back. The polar plot that you see here is symmetrical. Both halves, or it's actually quarters, because left and right and back and front are the same. Okay, if we wanted to do add directivity on the back, we'll have to add inline lines to that, either Enfire or Radiant. Okay, one thing we can do on PA Calculate is to add an arc, which we can do mechanically or electrically. If it's electrical, then we'll use delays that become larger as you go to the outside of the array. The angle can also be negative. And we can arc the array either mechanically or electronically. Let's go back to 0. The difference between mechanical and electrical arcing is not very much, and it's normally a lot more practical to do it electrically, plus the array takes a lot less space. Okay, let's look at rotation, because now there's a significant difference between doing it mechanically and doing it electronically. Say we had a vertical column of subwoofers and we wanted to aim it down towards the audience area. If we do it electronically, we can see that there is a front lobe which is pointing down 20 degrees in this case, but there is also a lobe pointing down 20 degrees downwards at the back, which might not be a good thing if we have neighbors in the back or noise contamination issues. So if we wanted to avoid these problems, then we would have to switch to mechanically steering the array, and in that case the back lobe is pointing upwards, and that could help with those noise contamination issues. Okay, we can combine both arcing and rotation, and perhaps we could do electronical arcing and mechanical rotation. And this could be maybe useful for left-right arrays if we want to steer the arrays to the outside to avoid left-right or minimize or reduce left-right cancellation. Okay, so let's zero the arc and the rotation, and let's now look at inline. which, like we mentioned before, we'll use to add directivity here in the back. Basically, we can add lines of end fires. Now we have one, and you can see very clearly that we've lost a lot of level here in the back. We can use an isobar display. Here's your main lobe, and there's nothing here, or there's barely little here in 180 degrees. Whereas if we take the inline off, then you can see the back lobe here at 180 and 180. Okay, so as well as end fire, you could use gradient, in which case some of the elements will have polarity inversion. Here, this envelope icon will let you email the table to yourself or somebody else for reference, or also for saving to a file. On iPhones, this is a bit of there's a bit of an issue in that the line breaks will show either as a funky tag, or if you take the encoding off, then you'll have all of the table in a line, but that's unfortunately a security issue on iOS devices. Okay, so as usual, comprehensive help on what's going on, and I think that's it for me for now. I probably missed a few points, so if you have any questions, just please ask in the comments. I'm using kind of a desktop version of the app. If you had a tablet, it would look relatively similar to this. On a mobile phone, if you hold it vertically, then you'll have the different elements aligned vertically. If you turn the phone sideways, typically with modern phones with a large screen, then you'll be able to see something similar to this with two elements side by side at a time. Okay, thank you for listening, and see you next time.